Hello and welcome to this lecture on quantum computing. It's time to start looking at algorithms that might actually be useful for someone. The kind of algorithms that we can use for real-world applications and to solve certain problems. Or at least we will be able to once the technology matures to a sufficient degree that the hardware can run useful examples of these algorithms. So this is in distinction from the proof of principle algorithms we looked at last time, which were just there to show us that there's something interesting in these qubits, and instead they're ones that we can relate to actual problems. So we start with the Fourier transform. So the Fourier transform is something that you probably already know about. You take a function and then you put it in this wonderful integral, and you pop out with another function, this time of a different variable that you get from these complex exponentials inside the integral. And this gives you information about frequencies going on inside the function. So for example, if the function is a sound wave, then you're going to start getting information about the frequencies of sound involved there, which you can use to analyze and manipulate that sound. And in fact, the sound you're hearing now would have been manipulated by Fourier transforms, not least at the point where I put it in the video editor and click on suppress noise in order to try and get rid of the fan noise, which already I can start hearing quite loudly at the moment. But anyway, let's move on from that. So yeah, Fourier transforms are great. Can we do them with a quantum computer? Well, more fitting to what a quantum computer does is the discrete version of a Fourier transform, where instead of having a function which gives you various values f of x for particular values x, we are going to have values fj corresponding to basis vectors labelled by integers j. And so we're going to use the vector f to represent a general set of data encoded in a vector in this way. And no, I've used Dirac notation here to represent these vectors. It doesn't necessarily have to be a quantum state that we're thinking of here, just using a vector to represent some discrete data that we want to do a Fourier transform on. And what the Fourier transform does is take any basis state j and transforms it to, well, this. So what's going on here? Well, it will help us if we scroll down a little bit, because one thing we should note is that these j are numbers written in binary. So we could have 0, 1, 2, and n is the number of numbers we are considering, the number of entries in our vector. So we go all the way up to having n of these basis vectors, and these are represented in binary on some sufficient number of qubits. So we use little n qubits such that n equals 2 to the n, so we're getting enough basis states, and so 0 is encoded as the state with all the zeros, 1 as mostly zeros but then a 1, and so on and so forth. So this is what these states mean. So when we go up and see these j's, we can remember that they're actually n qubit states for some arbitrary n. So we're taking some n qubit state, which is just a binary representation of some number, and from that we are getting the corresponding Fourier transform state, which in all cases will be a superposition of all of the basis states with various phases in here. So here these omegas are roots of unity. They are e to the I 2 pi over n, and then we raise that to the power of j times k, where j is the basis state that we are performing the transform on, and k is the basis state that this phase is going to go in front of. And that j times k is just number times number. Nothing too complicated there. So if we substitute that into our general vector, we find it transforms general vectors in a big, horrible way. but it's just to have it there. Okay, let's move on to the next slide, and you'll notice that I'm presenting this in a bit of a different way to previous lectures. There's a lot of equations to write down, so I previously wrote it all down, and now I'm going to comment on it. So for a general z-basis state, of course, we can write it down in terms of different bit variables in terms of for all of the different bits. So for some j, which can be written as a bit string, we can use j1 to refer to one of those bits, j2 to refer to the next of those bits, and so on and so forth. But usually with Qiskit, we do this a bit different. So we would usually be using j0 over on the right, and then j1, and then all the way up to jn-1. So that is the normal convention that we use with Qiskit, because it represents the way that we actually think of the numbers. The subscript represents the power we raise the 2 to, which is the base in this case. But in the maths that we're going to do today, doing it this way doesn't really make our lives easier, because we're actually going to be working more with fractions than with integers, and well, with fractions it makes more sense to go the other way. So for that case, we are just labeling our bits differently in this case. So when we write down what j is in binary, it means that it's a little bit more awkward, because the bit jl corresponds not to 2 to the l as it does in our normal ordering, but 2 to the n minus l. But, you know, it still works. So the reason why this is nice is because if we are doing it with a binary fraction, which means a number less than 1 expressed in binary, then we can, well, you know, the way we write down a fraction in decimal is to do 0.792654, whatever. Similarly, in binary, we can have 0.1011101. Now, we can express numbers less than 1 in binary in the same way. And so we are going to express it like this, where the most significant digit is j1, and then j2, and so on. And then for this fraction, we get the nice way of writing it down. JL corresponds to 2 to the minus L. So that's why we're using that the most significant digit has the least index, because we're mostly going to be working with fractions. Okay, now with this in mind, we can further investigate what the Fourier transform basis actually looks like, and use that insight to try and work out how to actually perform this basis transformation, taking states expressed in the computational basis or superpositions thereof, and turning them into states of the Fourier basis or superpositions thereof. So we start off with our Fourier transform basis state of some state j, and that is written in this way. We've got a normalization, we've got a sum over all of the basis states and the basis states, and we've got the phases which depend on the basis states that we're summing over, and also the original j. Now, one thing we can do is express this k in binary. So here we're using the fact that if we express k in binary, it looks like this, which has this 2 to the n in here. So if we divide k by 2 to the n, which is also known as 2 to the divided by big N, then we get this much simpler expression, which is just basically we've shifted everything the other side of the decimal point. And inherent in this omega is such a 1 over n. So when we also take this omega and turn it into its e to the I 2 pi over n, then we can just combine those, and that gives us this form, e to the I 2 pi times j times this binary fraction. And then we also express the k in binary in the state as well. So this is the tensor product of k1 on the qubit to the left, then k2, and then k3, and then so on and so forth. Also, when we do the sum over k, we have to split this into many sums, so n sums into sums over a single bit. Okay, so we've done that. So now we can use the fact that this is a tensor product to represent this more succinctly as a tensor product, so the tensor product overall L of KL. But we can also bring these phases in here because these phases depend on L in the same way. Yeah, once we bring those in here, it means that these many sums over a single bit can actually be exchanged in order with the product using a standard relationship between sums and products in order to have that we first do the sums over each of these single bit states and then tensor product that summiness all the way over all of the qubits. So this, in the end, gives us this expression, which is just a tensor product with lots of single qubit states, and the single qubit states are 0, plus, and this particular phase. So the interesting thing is that even though we had a big superposition to deal with here, it did not result in an entangled state. We start off with a product state, a state which is not entangled, which is just the tensor product of zeros and ones representing a specific binary number. And we transform that with the Fourier transform, and we get another product state. This time, all of the states are superpositions, or at least we think of them as superpositions in the Z basis. I mean, everything's a superposition in some basis. But yeah, they're superpositions, and the phases encode some information about the J that has been Fourier transformed. And it's not simply that each bit of J controls the phase of that particular bit of the Fourier transform, but information about all of the bits are actually spread over all of the qubits in a way that's going to be quite useful to us. So let's move on and take a bit closer look at that. So yes, it turns out to be this product state, but how are we going to create this product state? Well, for that, let's take a look at J and convert that into binary. So we see that we have J times 2 to the minus L for different values of L. So for one state, we're going to have J times 2. And for the next state, J divided by 2. For the next state, we're going to have J divided by 4. For the next state, we're going to have J divided by 8. Because we've got this J times 2 to the minus L, which is J divided by 2 to the L. And so we're going to have J divided by all the different powers of 2. So if we think of what J looks like in binary, again using this little endian convention, then if we divide by 2, what it does is it moves us one step along with respect to the decimal point, just like dividing by 10 in decimal. So we get J point blah 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 blah, J1 blah 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 to Jn minus 1, then the decimal point, and then we get the other side, Jn. So we can say this is an integer plus 0.Jn. And the fact that it's an integer is important here because when we have, what we have here, which is e to the I 2 pi, times the J times 2 to the minus L, then when we've got e to the I 2 pi times an integer, then it's the same as e to the I 2 pi times 0. It doesn't matter what integer is in there, even if it's 0. So really, the only part of all of this that matters is the 0 point and then the fractional part. Similarly, for J over 4, we're going to end up with an integer, and we're going to have now 2 bits in our fractional part, and so on and so forth. So depending on the L, then it's only L many bits that are actually going to be important for this phase. So for the qubit that has L equals 1, only 1 bit is of the original input, the thing that we are transforming, is going to be important. For L equals 2, it's going to be 2, and only for L equals n will it have effects from all of them. Okay, so let's move down, and you can see the more general form, although That's fairly obvious, I would have thought. So the more general form is just j divided by 2 to the L, and then we have these L bits. Yeah, and then we can write it in this way in terms of these fractional forms. So one of the qubits only has 0.jn. It only depends on that bit. The next one has 2, and so on. So with this product representation, we can see how to perform a Fourier transform. We just have to find some ways to make each of these particular states using those particular bit values to construct the right phase values. So for the leftmost qubit, for example, the phase in the superposition is this one, e to the I 2 pi 0.jn. And so this is going to be +1 or -1, depending on whether j is even or odd, because the 0.jn is either going to be 0, because it's 0.0, or it's going to be 0.1, which in binary is half. And that half would then cancel the 2. So if it's it's either e to the I times 0, in which case the whole phase is +1, or it's e to the I times pi, in which case the whole phase is -1. So it depends completely on whether this value of jn is 0 or 1, which is basically whether the number j is even or odd. So we start off with the state in which the number j is encoded in binary. So we have a qubit which is jn, and the way that we get the Fourier transform basis state that we need at the end will be simply to apply a Hadamard to that jn. And there we go. Now there's one bit done with a Hadamard. And it should be noted that if you look at this for the case of a single qubit, what is a single qubit Fourier transform? It's just a Hadamard. The rest depend on more than just one qubit, so we'll require controlled rotations, and these are going to be Z rotations because we're setting up phases. Specifically, we're going to think of our Z rotation as looking like this, and this is going to be our corresponding RK. So you can use it as an exercise for yourself to work out what that corresponds to in the kind of Z rotations we've seen so far, so what kind of angle you need in there. And if you get it wrong first time, try dividing by 2. So with that in mind, this is basically the circuit that does what we need. So we already know that the phase that we need for this particular qubit can be done by just a Hadamard. And then similarly, we just use controlled rotations to build up these phases, because each of these can be thought of as some, like in this case, an e to the I 2 pi 0.jn minus 1 jn is equal to e to the I 2 pi 0.jn minus 1 times e to the I 2 pi. That's supposed to be a 2 pi 0.0 jn. So we can just take all of these contributions from each of the bits individually and create their corresponding phases, and we can do those by corresponding controlled rotations. So everything that is controlled on jn will be done by these rotations. Everything that's controlled on this second qubit will be done by these rotations, and so on. So here there is an R2, which doesn't really fit what we're doing here, because the 2 should be controlled on, it should reflect also what it's controlled on due to the way these things are defined. However, this is qubit 2, so really this should be, for example, R3 in there. And so then we would have also a controlled R4, which is controlled on qubit 4, controlled R5, which is controlled on qubit 5, all the way down to Rn. This one uses a Hadamard to do the phase from bit 1, and then use the controlled R2 to do the phase from bit 2, and so on and so forth. So this performs the Fourier transform, although it should be noted it also reverses the order because the qubit that has its phase depending entirely on the parity bit, the J0 bit, the JN bit, is the one that will originally be on the far right, but the Fourier transform version is on the far left. So I've kind of ignored that detail in what I've said so far. But there is this need to actually swap the order, which could be done by swap gates, or it could just be done by we're deciding to order our qubits the other way now, or something. So this is not a huge headache, so that's why we don't think about it too much. But basically, this is how you would do a Fourier transform. You have to use controlled rotations to engineer these phases that you know you need to have from the definition of the Fourier transform. So what is the complexity of this? How many gates do we need to apply in order to get this effect? Well, for the qubits that require dependence on all of the original qubits, all of the original bit values, you will need to do controlled knots with all of the bits. So if you've got n qubits, you're going to have to do a Hadamard on your own qubit, a controlled knot, or a controlled rotation, with all of the other bits. So that takes n. And then for the next one down, it only needs n minus 1, and the next one down needs n minus 2. So this is the sum that you've got yourself, and it means that it comes out as, what is it, n times n minus 1 divided by 2? Basically, it scales quadratically with n. So the discrete Fourier transform, and also its inverse, which you do by just reversing the angle of all of the rotations, can be implemented on a quantum state efficiently by a quantum computer. And for comparison, the fastest known classical algorithm is on the order of n times 2 to the n, which is exponentially worse. So, can we use quantum computers to do fast discrete Fourier transforms? Well, the answer to this is yes and no. And it's no because preparing a general state to be transformed is inefficient. You have to create a superposition of 2 to the n different data values. That is going to have a horrible complexity. So that complexity is then going to remove possibly all actual advances that you get from the actual discrete Fourier transform being faster. So you're not going to get a nice efficient algorithm for a discrete Fourier transform. However, if we have cases where we naturally have some Fourier transformed information, then applying the Fourier or the inverse Fourier transform to get that information out will be something that's efficient. So the quantum Fourier transform can serve as a useful subroutine within quantum algorithms. An example of this is phase estimation. So this is where we have a unitary that we are able to apply, and we know that it has eigenstates because of course it has eigenstates. Unitaries have eigenstates, and those eigenstates have eigenvalues, which because it's a unitary can be expressed as a complex exponential with some phase. And here we're writing it as e to the I 2 pi times some phase. So this can be written as some complex, some binary fraction. It can be a binary fraction because we can write it in binary if we like. And it's a fraction because of our choice to have this 2 pi out here. Again, as we said before, only the fractional bit is going to be relevant. So the idea of phase estimation is that we may have some unitary where we want to know a particular phase for a particular eigenstate. We want to be able to know what that phase is. We have the ability to implement the unitary, but we don't necessarily know how to write it down and what its eigenvalues are. So can we do that with a quantum computer? So here the binary fraction is t bits long, where t is simply the number of bits needed to represent this phase. So we are going to assume that we have the ability to not only do u itself, but also to do a controlled version of u, controlled on a single qubit. If that qubit is 0, then u is not applied. If that qubit is 1, then u is applied. We are also going to assume that we have the ability to prepare these eigenstates. So the eigenstate that we want to know the phase of, we are going to assume that we have the ability to prepare that eigenstate. This means we have the ability to apply the following circuit. We start off with a register in which we're going to assume everything is initialized as plus. Okay, so there's a hidden assumption here. We assume that we can do a Hadamard and rotate lots of zeros to pluses. We have a second register, so a second collection of qubits which are initialized in this eigenstate. And then we have our controlled operations. So this one is a controlled version of u to the power of 2 to the 0, which 2 to the 0 is 1, so u to the 1 is just u. So this is just a controlled u, but this is u to the power of 2 to the 1, so it's u squared. We're doing 2 controlled u's, or maybe we have the ability to do it all at once because of the structure of the oracle that we're using to do this. But in any case, we do that, and then we do all of the other powers until we get to u to the 2 to the t minus 1. Again, t is the number of bits required to represent this, and therefore it's also the number of bits, qubits that we have in the first register. So there's t qubits in the first register. So what do we get out as a state from here? Well, the only thing that's being done to the second register is identities and u's. Identity leaves it unchanged. U also leaves it unchanged because it's an eigenstate. So we get u here. The only place where something happens is on these supposed control qubits where we're getting phase kickbacks. So the phases we get as eigenvalues are getting kicked back to all of these. So the phase getting kicked back here is the eigenvalue of doing u once, which is e to the I 2 pi times phi. In this case, it's that doubled, or the phase is doubled because we have the eigenvalue squared, and so on and so forth. So why is that important? Well, let's write down what we have as this total outcome for the first register. So as we tensor product over the t qubits of the first register, let's do a tensor product indexed from t to 1, and then we get these particular phases with these 2 to the L minus 1s up in there. And we can think of what happens when we combine this fractional phase with these powers. So if we take this fractional phase and multiply it by 2 to the 1, then we get our number shifted past the decimal place. So one of the bits, the phi 1 bit, gets shifted. The other side of the decimal place becomes an integer, and so we're going to be able to ignore it. And then we get 0.phi2 all the way to phi t. For multiplying it by 4, we have 2 bits that get shifted, and so we have the rest that remain, and so on and so forth. So different phases are going to depend on different number of bits. One is going to depend on them all. The last one's going to depend on just the least significant bit. So where have we seen this before? Well, instead of talking about this fraction phi, let's multiply it by a suitably large number that we get an integer, capital Phi, and this suitably large number is of course 2 to the t, because there are t bits in this fraction, and that's how much we have to shift past the decimal place. Yeah, so we're going to be thinking about this integer as representing our phi now instead of the original fraction. And so then it's fairly straightforward to see that the outcome that we get from doing all of these conditional rotations is exactly a Fourier transform, and it's a Fourier transform of this integer phi expressed in bits. So by doing all of these controlled rotations, we have gotten the Fourier transform of the answer that we want, which is what this phase is. So all we have to do is perform the inverse of the Fourier transform, which we just do by doing the rotations in the opposite direction, doing the gates in the opposite order, and there we'll have it. We will have the number that we want written in binary in some qubits. All we have to do is do Z measurements, get those bit values out, and we've got the number. The final state after the Fourier transform will be the answer we want, tensor producted with the eigenstate that we have prepared. Now there's a couple of rather strong assumptions here. First, we assume that the phase can be written down using a finite number of bits, so that there is some finite t, and also that we know what it is, or at least an upper bound, because that determines how many qubits we have in our control register. In general, this is not the case. If we don't know a phase, we don't know the phase. However, even if we use a value that is too small, it will still work. It will just give us an approximation of the phase instead of the phase itself. In fact, it's been shown that if we want to get the phase accurate to n bits with high probability, then we need to use a t, which is n plus some value, which depends on the accuracy epsilon that we want to have. So this is an efficient scaling. However, can we use this phase estimation for anything useful? Is there ever any time that we actually want to get these phases out? So you might think one application is physics stuff, probably. And yeah, that's true. But there are also applications that are abstract mathematical problems, and we'll look at one of those now. So order finding. Consider the positive integers x and n, where we are just taking the convention of using x to refer to the smaller one and n to refer to the larger one. And a question we want to answer is, what is the smallest possible integer r such that x to the r equals 1 mod n? So what's happening here? So we take x, and what is x mod n? Well, it's x. Okay, what is x squared mod n? Well, it's another number. What is x cubed mod n? It's another number. And so you keep on generating numbers until at some point you'll come to 1. And once you've come to 1, then what is x to the r plus 1 mod n? Well, you know that x to the r plus 1, that's not a very good x. Well, x to the r plus 1 is x to the r times x. And since x to the r is 1, at least mod n, then x to the r plus 1 is equal to x. So once you've found this r, you've found the periodicity of this process. Because then, after you go beyond that, you're back to x. And then you're back to whatever x squared was, and so on and so forth. You're going to keep on going through the same sequence of numbers. So this is called the order of x modulo n, and it's useful for stuff. Now it's believed that no polynomial algorithm exists to compute this on a classical computer, where polynomial means it has to have a complexity that is polynomial with the number of bits used to specify these numbers x and n, or we can just say the number of bits used to specify n, because that is the larger one. So, can we do it with a quantum computer in the way that is polynomial? For that, we consider the unitary, which applies this function. So it takes some number j and calculates x times j mod n for all of the possible basis states. Now here we have a bit of a strange case because, well, what about the case that j is larger than n, then x times j mod n is going to be a kind of weird thing to calculate. So we're just going to take the convention that x times j mod n is equal to j in those cases, because we don't really care what's going on up there. So we just fill it in with whatever. So we have some convention such that this is a valid unitary. It takes a set of numbers expressed in binary and maps those, each of them, to a unique set of numbers expressed in binary, so that it takes a basis from a basis. In both cases, the same basis, just numbers expressed in binary on qubits, but with just a reordering. So yeah, this is the convention we choose. So what are the eigenstates of this? Well, there's one eigenstate that's fairly obvious, which is the sum over the r values that you get from doing x to the k mod n for k from 0 to r. Because, well, one is going to give you 1, and the next one gives you x, and the next one is whatever x squared is, mod n, and x cubed mod n, and so on and so forth. And you get to the point until you've almost looped back. So you don't do x to the r, so that should actually be minus 1 there. So you've got all of the x to the r's. So now if you were to apply the unitary to this, what it would do is it would just multiply each of these by x, and therefore take x to the k to x to the k plus 1. And so it just basically iterates all of these states along one, but you go from having a superposition of them all to still having a superposition of them all. So you don't really change anything. Also, if you put a bunch of phases in, you can get similar eigenstates. So more generally, we can express the eigenstates like this, and I encourage you to take a look at them yourself, and also prove that the eigenvalues look like this. So basically, the eigenvalues have a phase where the eigenvalue for the state us has a phase which is s over r. So s is the number for the eigenvalue, and r is the number that we want to calculate. So for this, we need the ability to perform these modular exponentiations in controlled rotations, and there is a way to do that. So essentially, we just use the fact that we know how to do this classically in an efficient way, and we implement that as an oracle. There you go. Another thing we need to do is be able to prepare an eigenstate. So really, we want to prepare the eigenstate u1, because then the phase that we're going to get if we perform phase estimation is going to be phi equals 1 over r. And if we know 1 over r, we know r. However, if we don't even know what r is, we don't have much hope to prepare efficiently these, in general, highly entangled states. So, what are we going to do? Well, we can just note that if we look at the superposition over the first r eigenstates, so from u0 to u to the r minus 1, then, well, what do we have here? Each of these eigenstates is written like that, and we are taking the superposition over them. Now these two sums, we can reverse their orders, and once we do that, we see that the s dependence does not exist in the state, and so we just get that the coefficient of any of these particular states is equal to this sum over roots of unity. Now when we sum over roots of unity, then there are some useful properties we can use. So basically, if you sum over all of the roots of unity, then you get 0. So for example, if you take the two square roots of unity, which are 1 and minus 1, you sum them up, you get 0. If you take the four fourth roots of unity, which are 1, I, minus 1 and minus I, and you sum them all up, you get 0. For the third roots of unity, it's also true. If you think of the complex plane, you're always going to have some sort of an equally distributed distribution around 0, you sum them all up, they go to 0. So in this case, we are basically generating roots of unity. We are summing up roots of unity, and we are summing up the rth roots of unity, and we are summing up all r of the rth roots of unity. And the only time when we're ever going to get something that isn't 0 is when they are all just 1, and they will all be 1 if k is 0. So if k is 0, then we're summing up r times 1, which is of course r, and if it is anything else, then we get a 0. What this means is that this superposition over the first r eigenstates comes out as x to the power of 0, because 0 is the only one of these that actually survives. X to the power of 0 is of course the number 1, which is expressed in binary as 0, 0, 0, 0, 0, 0, 0, 1. So the superposition of the first r eigenstates is definitely something we can easily prepare, because it's just a whole bunch of zeros and a 1. Just need an x-gate for that. So rather than using a single eigenstate, we are using a superposition of eigenstates on the second register. So what's the output going to look like? Where we're going to get a superposition of these eigenstates entangled with their phase written on the first register. And these phases are all approximately equal to S over R, where S is the eigenstate and R is the order of x modulo n. And the reason why it's approximate is because we didn't necessarily use enough qubits to perfectly capture these values. So one thing we could do here is apply this method lots of times, so on the order of r times, in order to get all of the different versions and all of the different phases, and then deduce what r must be. But the number of such states is on the order of, well, it's 2 to the on the order of L, because of just the size of the number of these states that exist. So it would be inefficient. However, all we need is one phase, one randomly chosen one. So we can just look at this register in the Z basis, and it will effectively randomly choose an S and give us the phase S over R. And with that, we will already be able to work out what the order of S modulo n is. Well, as long as it comes out as prime, but there's a decent chance of that. So the way this works is that we use the continued fractions algorithm. And the continued fractions algorithm goes by this theorem that I'm going to scroll up to now. You can see that scrolling is incredibly slow, which is the main reason for all cuts in this video. And this tells us that if we have some approximation of a fraction, S prime over R prime, as long as that approximation is sufficiently close to the fraction, which is what this side tells us, then the continued fraction algorithm can compute S prime and R prime from phi in polynomial time, which is nice. So why am I using S prime and R prime here instead of S and R as I have before? Well, if we hit a particular value of S which has a common factor with R, then those common factors will cancel, and so it will suggest to us that the R that we get is something different than what it is. So we aren't going to get the actual S and R that where the S is the eigenstate and the R is the order of x modulo n, but we're going to get those two numbers but with any common factors removed, and that's why I put an S prime and an R prime. But nevertheless, we can get those numbers if it's sufficiently accurate. So how accurate is sufficiently accurate? Well, since the phase is accurate to n bits, then we can do basically a bit of maths, and show that the number of bits we need, and you just have to work through all of this. So what does it mean for something to be accurate to n bits? Okay, it's accurate to 2 to the minus n. So what we need is a number of bits which scales logarithmically with r, and that is fine. So that's kind of like the number of bits used to represent r. So the number of qubits that we need in order to get sufficient accuracy is on the order of the number of qubits we need to represent the two numbers that we started with, which is perfectly fine. When we have problems based on a particular number and we are going to use quantum computing, we expect at the very least to write that number down in binary using qubits. So the fact that we need on the order of that many qubits is great. So one problem here, as I've said, is that S and R may have common factors, meaning the S prime and the R prime are not the values that we want. This is solved by having an S prime and an R prime that don't have any common factors. Since we just get randomly assigned S's and can't control them, then we can't ask for the right value of S, but we can just repeat it until we get a case where they don't have any common factors. And we know that will happen when S has no common factors with anything. So basically, when we hit upon a prime numbered eigenstate, then we will get the right value of R out. And a prime numbered eigenstate will occur fairly often. Like, primes are not the most common thing in the universe, but they're not all that rare either. They occur with kind of a probability of 1 over log L. So at least you have to just repeat it log L times, and then you can expect to get a prime. Also, it should be noted that we can efficiently check whether a result that we have been given by this algorithm is correct, because all we have to do is take a given solution for what R is, so let's call it R prime, and then we can do x to the R mod n, and we can see if it's 1, because if it is 1, then that's what we wanted, and if it's not 1, then it's not. So we can very easily check if a given answer is correct, and then we know that we didn't hit a nice eigenstate. We can run it again, and then we just keep on doing this until we do hit a nice eigenstate, which shouldn't take too many repetitions. And that is basically phase estimation and its use for this quite abstract mathematical task of order finding. Now we're at the point where we can look at the factoring algorithm, as Peter Shor calls it, or Shor's algorithm, as everyone else calls it. So we have an efficient algorithm for calculating the smallest integer such that x to the r plus x to the r equals 1 mod n. But what about factoring? Well, to find all prime factors, it's sufficient to have an algorithm that can find a non-trivial factor for a given number, and then you divide by that number, and you repeat the process until you've extracted all of the non-trivial factors. We can also use primality tests to determine whether given factors are prime, so we know whether we can stop doing this process. So there are then two theorems that we can help us to build a factoring algorithm. One is that, and you probably don't need all of the details, but let's go through them. One is that if n is an L-bit number and y satisfies y squared equals 1 mod n, and y is somewhere greater than 1 but less than n minus 1, because there are trivial solutions to this. If y is 1, then 1 squared is 1 mod n. If y equals n minus 1, then mod n it's effectively minus 1, so that also squares to 1 mod n. But if we exclude those trivial solutions, then the greatest common divisor between minus 1 and n And also y plus 1 and n will be a non-trivial factor of n computable with complexity L cubed. Okay, why? Well, if y squared equals 1 mod n, then y squared minus 1 is equal to 0 mod n. We just took 1 from both sides. Now this means that n is a factor of y squared minus 1. And as such, when we write y squared minus 1 as y plus 1 and y minus 1, then all of the factors of y squared minus 1 of n have to be split between the two, so we will find common factors within them. Now, the fact that y is restricted to not being as high as n minus 1 and being greater than 1 means that that factor cannot be n itself. So computing these greatest common divisors of y minus 1 and y plus 1 of n and n will yield at least one non-trivial factor of n. And this can be done using the Euclidean algorithm, which is non-quantum. So as soon as we have a y which satisfies this, where n in this case is the number that we want to factor, then as soon as we have a y that satisfies this, we can use this to calculate a non-trivial factor. Now using this, then we just need to find that y and then compute these greatest common divisors and then keep on breaking this number down into its factors to get everything. And this will yield all primes in a time which is dependent on the number of prime factors and polynomial with L, because that's the amount of time we need to take y and turn it into these factors, and also the time required for y. Now, if we use only classical computation, then the time required to find these y's is not efficient. So what about with a quantum computer? Well, let's suppose we have an n which can be expressed with m prime factors or distinct prime factors. Each of those may have some multiplicity. Then for a randomly chosen integer x between 2 and n minus 1, the greatest common divisor the greatest common divisor between x and n is 1, so which shares no factors with n, then we can consider this notion of the order of x modulo n. And the probability that the order of x modulo n satisfies two conditions, that a, it is even, and b, that x to the power of r over 2 is not equal to minus 1 mod n, is 0,1, basically. The more factors there are, the more distinct factors there are, the more likely it gets. But even if there's only one distinct factor, it is only as bad as half. So it's a fairly decent probability. So if you randomly choose an integer, it's fairly likely to satisfy these properties for you. Or at least for a randomly chosen integer, the corresponding order of x modulo n is fairly likely to satisfy these properties. Why do we care? Well, if r is even, then x to the power of r over 2 is an integer. And it's an integer such that that integer squared is equal to 1 mod n. So it is our y, or is it? So one of the problems is also that our y has to exist within a certain range. But our other condition also makes sure that it does fit within that range. So these conditions are such that x to the power of r over 2 can serve as a valid y that we would use in finding a factor. So with 0,1 probability, when we choose a random integer and calculate the order of x modulo n and stick it into this equation, we will get a y that we can use given our previous theorem to find a factor. So that's all we need for Shor's algorithm. So let's just go through the steps of Shor's algorithm. So in this, the grey steps are ones that only use a classical computer, and the black ones are the ones that use a quantum computer. So step 1 is n prime, because if it is, you're done. So this can be done efficiently with a primality test. If it's prime, there you go. Otherwise, you continue. Step 2 is determine whether n is even. Well, you could also determine whether n is a multiple of 3 and a multiple of 4. This is going to take inefficient time to do, so you don't check all of the factors. But there are some things where you need to assume that it is not even, so you at least check if it's even. If it's even, then you know a factor is 2, and you output that. Otherwise, you continue. Okay, step 3, determine whether n is of the form n equals a to the b, where a is greater than or equal to 1 and b is greater than or equal to 2. So does it only have one distinct prime factor, and it's just the power of that? If so, output that one distinct prime factor. And this can also be done efficiently. Otherwise, continue. Step 4, we prepare for Shor's algorithm. So we randomly choose a value x in the range from 2 to n minus 1 and calculate the greatest common divisor of x and n. If the greatest common divisor of x and n is greater than 1, then we have found a factor. So that's good. If not, then we have an x which has no common factors with n. So we find the order of x modulo n, which we do, of course, with order finding. And if r is odd, or x to the r over 2 mod n is minus 1, then we can't continue. We have to try again with a different value of x. Otherwise, we set y to be x to the power of r over 2. Next, calculate the greatest common divisor of y minus 1 and n, and the greatest common divisor of y plus 1 and n, which is efficient using the Euclidean algorithm, and output those lovely factors. So this algorithm succeeds when the number does not require the quantum part, or if the number requires up to the quantum part and outputs an r that satisfies these conditions, which, as we've said, is O1. So it succeeds with O1 probability, which is cool. And then I press the button for a new page instead of next page. So basically we found that we've got an efficient way of computing R. We've got a way of factorizing numbers. Let's look at a specific example to finish things off. Factorizing 15. So step 1, 15 is not prime. Step 2, 15 is not even. Step 3, 15 is not a power of a single distinct prime factor. So we continue. Step 4, let's consider the case that x is equal to 4. So that's our randomly chosen value. The greatest common divisor of 4 and 15 is 1, so they share no factors. So then we move on to the quantum part, and we need to find, well, what is the order of 4 modulo 15? Well, 4 squared is 16, which is obviously 15 plus 1, so that is 1 mod 15. So r is the order of 4 modulo 15. So the y and r is even, so the y we can use is x to the r over 2, which is x to the 1, which is 4. And then what is 4 plus 1? 5. What is the greatest common divisor of 5 and 15? Well, 5. What is y minus 1? 3. What is the greatest common divisor of 3 and 15? 3. So there we go. Those are our two factors. We have factored 15, which is the number that was first factored by a quantum computer, and it's actually the first number that can be factored by the quantum part of this algorithm, because if you go through all of the other numbers, 1, well, that's boring, 2 is even, 3 is prime, 4 is 2 to the 2, 5 is prime, 6 is even, and then it goes down to 3, which is prime, 7 is prime, 8 is 2 to the 3, 9 is, what is 9? Oh, 3 squared, so that's one of these powers. There, it gets caught by step 3. 10 is even, and then you remove that and it becomes 5, which is prime. 11 is prime, 12 is even, and you strip out those two factors of 2, you get 3, which is prime. 13 is prime, 14 is even, and you go down to 7, which is prime. 15, well, it's this one. It's the first one that has two distinct I was going to say non-2. I mean two distinct odd factors, which are 3 and 5. And then you can start thinking about what is the next number that would need the quantum parts of Shor's algorithm, and so on. But this is Shor's algorithm. We have gone through Fourier transforms, phase estimations, order finding, and Shor's algorithm today. I think we're going to leave it for this lecture. Thanks for listening.